Okay, so it's my pleasure to welcome Marc Levine, currently of Northeastern University, sadly soon to be of Essen University. Is it University?
University Duisburg-Essen.
Ah, yes, I won't say that. University of Essen in Germany. So this is like his farewell talk to the Boston area. He'll speak to us today about the Motivic fundamental group.
Thank you, David. Thanks very much for inviting me. It's a pleasure to be here. What I want to tell you about is basically an interpretation of the work of Levine and Goncharov on Motivic pi 1. And I should say at the beginning that a lot of the results that I'm going to talk about came about through many discussions with Elaine and No at Essen. Okay, so I want to talk, first of all, the fundamental sequence of Grothendieck fundamental groups. And the topological version of that is if you have a fibration sequence. So one example would be that E is a fiber bundle over B with fiber F. That's an example of a fibration sequence. And we fix some base point X in F, and we follow it along to get a base point in each of the spaces. Then that leads to a long exact sequence in homotopy groups, and I just want to look at the part of interest pi 1. Now, under some conditions, this actually is just one chunk of the sequence. In other words, we can put 1s here and 1s here if we make some assumptions, so under some assumptions. So for example, if pi 2 would be 0 and if F is connected, pi naught. Okay. Now the analog of this in algebraic geometry is the fundamental exact sequence for Grothendieck fundamental groups, algebraic fundamental groups. So now let's say we have X, some variety over a field K, and we choose a point X. What plays the role of a base point is a K bar valued point of X, K bar being the algebraic closure. And then we have, we can extend X up to the algebraic closure. And X also will form a point in X bar, and this will lead to the following sequence, which does have the 1s in it. We have the pi 1 I'm writing now, let me put a little G here for this is the Grothendieck pi 1 or étal pi 1. And this group here, just to tell you what, I won't define these really, but this group here is just a familiar Galois group of the algebraic closure of K over K. Now this one is often called the geometric fundamental group. Pi 1 geometric. And the reason it's called the geometric fundamental group is, in fact, if you extend, let's say K is inside of C, and you extend, so K bar is inside of C, and you just extend up to the C points, then this is just equal to the profinite completion of the usual topological pi 1 of the topological space you get by taking the C-valued points at X. So it's closely related to something from topology. And you see that this thing in the middle here is a mixture of the two. For example, if you have if X happens to be now a K point, then you get a splitting here, and that gives an action here. It makes this group a semi-direct product. And you see somehow this group is, in any case, even without that, it's somehow built out of the topological data given by the geometric fundamental group and the Galois action on it defined by this sequence. Okay, so our goal here is to try and unite these two pictures. So what do I mean by that? Here we have something defined for topological spaces. It's not really defined for algebraic varieties. Here we have something defined for algebraic varieties, but there's a compatibility with the topological picture in that in the geometric setting, we're getting the profinite completion of the topological story. So what would be great would be if we could get somehow this gadget working for algebraic varieties, and which would give you some interesting sort of Galois action on these things. Of course, that's not possible. There's no really nice way to have the Galois group act on fundamental groups like this. So we're going to have to make a compromise, and the compromise, so we unite these, we make a compromise. Rather than taking the profinite completion of the fundamental group, we take the Malchev completion. So what we'll get under some, at present, rather restrictive assumptions, unfortunately, is a third sequence, a third construction of a group, which could be called the Motivic, this is the Levine-Gontarov Motivic fundamental group, which somehow it's a unipotent group, and its profinite completion will be related to this thing, and it'll be related to the profinite completion of these, to the unipotent completion of these things. Okay. But it'll also have some additional action of some other unipotent type group which comes from the base field. So it puts all these pictures together. Okay, so before I do that, let me review the Malchev completion. Let's give a review of this, of the Malchev completion. A quick review of it. Okay, so how does that come about?
Because it's a review because we've all seen it before.
Yeah, this is well known, right? This is the review. Okay, right, absolutely. Okay. So the Malchev completion comes from the following formula, that if you have some, let's say you have a space M and some point 0, and we want to compute or get some idea of what pi naught or what pi 1 is, well, we can do the following thing. We can take the loop space based at the point 0 of M. This is just sort of pointed maps. And I'll write maps of what? Well, it's S1, but I'll write that as the pair, the unit interval with the endpoints maps into M with its base point. In other words, maps of the interval into M that sends 0 and 1 to the base point of M. That's a space. So there's a topology on that. And then what is pi 1 of M? It's just the connected, the path.
I interrupt for 2 seconds. We've got a different radio frequency coming in. Marc's, so I might just get Marc. Would you mind switching?
No, go ahead.
Can you just switch this frequency?
Or can you switch, flick from A to B? Sorry. Yeah.
How's that? Okay.
Just trying to
Let's see. With that
I'm sorry,
minor.
you're being interrupted by builders.
Okay. All right. So this is just the space of path components in the loop space. That's almost by definition of the loop space. Right? We're looking. These are loops, but we're not. And these are loops up to homotopy, which is pi. Okay. Well, okay. What does that tell us? I mean, it doesn't help too much. But the idea is, well, now if we want to, instead of getting pi 1, let's get the group ring of pi 1. Well, this should be the group ring on this set where there's a multiplication gotten by composition of loops, but let's forget that. What's the group ring of the connected components, or what's the free abelian group anyways on the connected components? It's just H0 of this space with Z coefficients. Okay. And now if we want to get, well, this thing has a structure of a Hopf algebra. It has multiplication just by multiplying the coefficients. I mean, by, you know, it's a ring, so you have the multiplication. It has a co-multiplication, which is sort of a diagonal co-multiplication. And so you can take, you can dualize a Hopf algebra. Let's say, make it with Q coefficients, because I want to dualize things nicely. So the dual Hopf algebra, which are just the Hopf algebra of functions on this kind of group, will just be the H upper 0. Say with Q coefficients. And so this thing will have some Hopf algebra structure. Okay, so the remarkable thing is you can actually almost get this Hopf algebra just from the de Rham complex on M. Maybe not with Q coefficients, but with real coefficients. And if you work with the singular cochain complex with Q coefficients, you can recover this Hopf algebra. So let me explain. Not quite, though. This is where the completion comes in. Okay, so now let's go back to our definition of the loop space. What is this? Well, it's maps of the interval into M. But let's say we have some generic base point, and there are two maps of this generic base point into the interval. One goes to 0, and one goes to 1. And now we have our generic base point here. And now there are two maps into M, and they both go to the given base point 0. Okay, so now a map of the interval into M, which sends 0 to the base point and 1 to the base point, is just a map, let's call it F1, and there are not too many maps here, let's just call it F0, such that this diagram commutes. So the collection of all such pairs, F0 and F1, is just equal to the loop space, the base point 0. Now let me add some extra things which don't look like they're too useful. You can, of course, project this to the point. You can project this to the point. That doesn't change anything. Now you can do the following funny thing. You can, the interval is the 1 simplex. And you can continue this diagram, the 2 simplex. This is a triangle with 3 faces. You have the 3 simplex, etc. And, well, there are 3 faces in the triangle. And there are 2 ways of collapsing the triangle back down to its edge. And this picture continues, etc. And, in fact, you can do the same thing with M. You can take M squared. And of course, there are 2 maps. Well, what are the 2 maps? Did I do something funny here? Well, let's see. There are certainly, what are a bunch of maps here? I can send M to 0M, or I can send it to MM, or I can send it to M0. So that's the 3 maps. There's this. And then I have 2 projections. That gives me 2 maps like that. So let me just write down what the first maps are. M here, just so you see it, M goes to, the first one sends it to 0M. The second one sends it to the diagonal MM. And the third one sends it to M0. Okay. So instead of looking at pairs, you can look at triples. Zero.
Even go up another dimension.
Exactly. You can keep on going up. And the theorem is no matter where you go, you get something which is homotopy equivalent to the loop space. So you can keep on going all the way up. It doesn't matter. So if I just change that from equals to homotopy equivalent, that's still true. And now remember, we wanted to calculate H0 of the loop space of M. Well, I could just concentrate on this diagram here. How do I calculate cohomology? Well, let's use our singular cochain complex. That's some functor from spaces to complexes of, say, Q vector spaces if we use Q coefficients. So we can apply that. It's a contravariant functor, so we can apply that functor to this diagram. So we apply the functor, the singular cochain complex with Q coefficients, and we get, instead of a diagram like this, we get a similar diagram where all the arrows go in the opposite direction. And I'll omit the things opposite to these funny arrows. Those don't really interest us anymore. So we have the point with Q coefficients. Of course, that's a rather simple gadget. And then we have two restriction maps, the two restriction maps to 0. And then we have three maps like this, etc. Okay, we can continue that. And so this thing should calculate for us the cohomology of this space. And well, how does it calculate that? If we have something like this, what do? You take alternating sums of these maps, and then you use the Kunith formula that tells you, well, this thing is essentially just Q. These two maps are the same, so the alternating sum of this is just a 0 map, so that's not doing anything. And here I have C star of M, Q coefficients. The Kunith formula says this is the tensor power of it with itself. And here I'm taking alternating sum of these maps. Do the same thing here. And I get C star of M, Q tensor 3, etc. So what I have is a double complex. I take the total complex of this thing, and this is called the reduced bar construction on this gadget. Okay, now what structures do I need on this gadget to make this? It turns out to make these, when I make this identification, that's gotten by using products. Right? I take the product of the two pullback maps. So you need products on this in order to make this make sense. So if you have any complex with a product on it, such that the product is graded commutative and has the Leibniz rule with respect to the differential, you can form this reduced bar construction just by doing this gadget. And the theorem is that the H0 of this, okay, is not quite what I want. What you'd expect is that the H0 of this bar complex computes H0 of the space I'm talking about, which would be the rational dual of the rational group ring. The theorem is, so this is due to many different people. Maybe Alex, you can tell me, I don't know who it's due to. Sorry. Is that the H0 of this bar complex is isomorphic to the following thing. You take the group ring on pi 1, and instead of taking, it's not going to be the dual, you have to mod out by various powers of the augmentation ideal. So you can map this ring to Q by sending all the group elements to 1. The kernel of that is the augmentation ideal. You take its powers, you take the dual of this, and by taking higher on higher powers, you're taking an inverse limit. When you dualize, you get a direct limit. And this is what's called the Malchev completion, or its dual, depending on what you're looking at. So it's one version of the Malchev completion. Okay. The representations of it's actually has a natural structure of a Hopf algebra, which you can recover the Hopf algebra structure from geometrically defined operations on this gadget. So it's a Hopf algebra, and the comodules over this Hopf algebra are essentially give you what are called the unipotent representations of the pi 1. So this gives you the unipotent, it's sort of unipotent representations of pi 1 come from this Hopf algebra. So you don't quite recover all representations of this group. In other words, you don't quite recover the group back, but you recover some some quotient of it. Now, if you think about representations of pi 1, what does that give you? It gives you local systems on the space M. So these are giving you local systems, let's say finite dimensional, with finite dimensional fiber, that have a natural filtration such that the quotients are trivial local systems. That's another way to say what this is telling you. So it's telling you that part of the representation theory of pi 1. Okay, so that's topology. So now we want to do this motivically. So the motivic version, so that was part 1. Now we want to go on to motives. So motivic version. The idea here is replace this. We do the same thing. We replace M with an algebraic variety X. We consider the same gadget, which makes sense in the algebraic category. But then we have to say, what is this gadget? What is the cochain complex functor? We don't want to have to take a topological space by taking, say, C points or R points. We want to do a universal, purely algebraic gadget. So we replace the functor, the rational cochains, with sort of the universal version, or algebraic varieties. And this is achieved, well, we don't know what that is exactly, but in the strong sense of this being complex of abelian groups, in other words, complex in an abelian category, we don't have that. But we do have something which formally looks like a complex, even though there's no, up to now, underlying abelian category. And in some cases, there is an underlying abelian category, which we'll need when we want to pass from this gadget, which is a complex, to this gadget, which is its cohomology. So this, in other words, this lives in the category dm over your base field K, and then under some circumstances, under some conditions, we can restrict to a subcategory the category of mixed-Tate, triangulated category of mixed-Tate motives, which sometimes is known as a cohomological functor H0 to an abelian category. And then we can just formally take H0 of the bar complex, and that gives us, that's a Hopf algebra, and the resulting group object will be our motivic pi 1. Okay, so that's the program. So let me say a little bit about this category of Vojevodsky, the triangulated category. So this, by the way, just so to orient you, in the topological picture, this plays the role of the derived category of Q vector spaces, or abelian groups, say, abelian groups. This is the place where complexes live. This plays the role of sort of special complexes. So they have special properties. Those are the ones we can handle. And this guy will kind of play the role of the abelian category of abelian groups. So just so you have the analogies present. Okay, so the derived category is what's called, is a special case of a triangulated category. That's where you can't talk about kernels and co-kernels, but you can talk about exactness in what's called exact or distinguished triangles. Okay. So without going into the whole theory of these things, let me just tell you how you build Vojevodsky's triangulated category of motives over field K. Let's say perfect, well, the definition makes sense for any field. Okay, so we first define the category of smooth correspondences. Okay, so what is this? The objects are the objects in the category of smooth varieties over K. In other words, smooth varieties over K. All right, and what are the morphisms? So the morphisms from any x to y, first of all, it's not a set, it's going to be an abelian group. Well, it's a set, it's going to have the structure of an abelian group. And what abelian group is it? It's the free abelian group on the set of irreducible subvarieties inside the product. So W is irreducible. And if I project to x, if I project into x, this map is finite and surjective. Well, I mean, if x itself is not irreducible, that's not possible, so surjective on some component. Okay. And those are going to be the Homs. Now I need a composition law. So the composition law goes like this. So I take some W in here, let's say two formal sums of these things. And where do I send this to? I take the projection on the first two factors. I pull back W. So, I mean, what am I doing? I take W cross Z, and I intersect it with X cross W prime. There's a well-defined intersection product between these two. And then I take the projection onto the first and third factors, onto the X cross Z. Okay, but you say this intersection product is not always defined, and I didn't say that Y was proper, so this projection is not defined. Okay.
These are your morphisms?
These are going to be the morphisms, that's right. But I have to define, it's just a category, so morphisms are an abelian group, and I have to define composition. So I'm defining composition for you right now. So this is the composition. You take the theorem is the assumption that the W was finite over X, and then this W prime will be finite over Y, forces us to conclude that this intersection product is automatically well-defined. There's no components of improper intersection. And the locus of the set theoretic locus of the intersection will be finite over X cross Z and finite and surjective over X. So in other words, the push forward is then well-defined, and it gives you an element in the correct group. So that's the composition law in the category. All right, so now I have a nice additive category, and in fact, it's a tensor category. It's an additive category. Direct sum corresponds to disjoint union of varieties, and there's a tensor operation corresponding to just product over K. So it's really a tensor category. All right, so now I do a little bit of categorical fancy footwork. Okay, now there are a number of ways to proceed here, but let me do the fancy way. You define the category of PreSheaves with transfer. By definition, it's just a category of additive PreSheaves of abelian groups on this category.
Where are the triangles?
There aren't any yet. We'll get there. We're not there yet. This is an abelian category. So what's a PreSheaf? It's just a contravariant functor from this category to abelian groups. And additive means it sends disjoint union or direct sum to direct sums. Or products or something, because it's contravariant. Okay. Sends direct sums to products. All right.
And if the unionism disjoint?
Then I don't care. Because everything is smooth, so there are no non-disjoint unions. All right. So now inside this category, we have the category of PreSheaves, which are sheaves. So let's call that sheaves with transfers on K. This is Motivic sheaves. So what does this mean? Well, I mean, I'm not going to go into the whole business of what a Grothendieck topology is. This Motivic topology is a Grothendieck topology on smooth varieties. And smooth varieties actually maps smooth varieties over K embeds inside this category by sending, well, the objects are the same, so you send X to X, and if you have a morphism F from Y to X, you send it, or sorry, from X to Y, you send it to the graph of the morphism inside of X cross Y. And since the projection to X is actually an isomorphism from the graph to X, that's a good object giving you a morphism from X to Y in this category. So now if you have a PreSheaf on this category, you can restrict it to get a PreSheaf on this category. And the requirement that you're in this subcategory is that when you restrict it here, it should be a sheaf for this topology, whatever this topology is, in some sheaf condition. Okay. And now we can just take the category of complexes on this category of sheaves, and then we can, then we can take the derived category. This is complexes. And then we take the derived category. This is an abelian category. This is just its derived. So in other words, it's complexes where you invert maps which give you a quasi-isomorphism, which induce an isomorphism on cohomology. Okay, and this is a triangulated category. The triangles here come from the cone sequences in this category. That's a triangulated category. Now, what you can do with a triangulated category is you can localize. Localize is a nice procedure which, in other words, to localize a triangulated category, you select a collection of objects which you want to make isomorphic to 0. And that, if you want to require that the resulting object is still a triangulated category and the map is a map of a functor of triangulated categories, that generates a certain subcategory called a fixed subcategory. That kills all those automatically, and what you get is the localization. Now, in fact, we want to assume not only do these, since this is rather a big category, I'm using unbounded complexes, we want to assume that not only are, when I kill something, that all triangles I can build out of it get killed, but also all direct sums of things which die. So that's a technical property. So I'll just say localize with respect to the following things. Well, we have special objects. Remember, this sits inside of here. We have a PreSheaf, which is just a representable PreSheaf. So with respect to, I forgot to tell you this. So what is ZY? ZY is a representable PreSheaf. ZY on some T is equal to the Homs in the category, core of T into Y. It's the representable PreSheaf. It turns out it's actually a sheaf. And that gives a functor from smooth varieties to this category of PreSheaves. And so since I map X cross A1 to X by the first projection, that gives me a map on the representing sheaves. And so what I do is I take these complexes and I make them 0 in such a way.
You're localizing it, something that becomes 0?
Yeah, I localize. It means I take all these complexes and I make them 0 in a nice enough way that the resulting object is still a triangulated category. And that's what I call the category, or that's what Voivodsky calls the category of effective motives. Okay, so we're almost there. Then there's one more step. There's a special object here. If you take the projective line, you can of course map it to this representing PreSheaf for a point just by the projection. And you can take this guy. This is a map of sheaves, so it has a kernel. That's sheaves. So you take the sheaf kernel, and then you take this and you shift it by -2, and you call this thing 1. This is the Tate object. It turns out that the tensor structure on here extends to a tensor structure on here, and you form the new category by inverting operation of tensor product with Z of 1. in a nice enough way. There's also some technicalities here, and that gives me the category I'm after.
So this is all algebraic.
This is all algebraic.
You don't have any schemes, you don't say you don't...
Well, the schemes are right at the beginning. There are the schemes, smooth varieties over K. Then I do some homological algebra to that. That's right. All right, so that's my gadget, which is...
Not that I'm
yeah.
everything anyway, but why do we want to invert that?
Okay, right. So let's say, why do we want to do this?
Just the last
Okay, no, well, first of all, I'll tell you why. This thing, okay, let me just say why. First of all, why do we pass from PreSheaves to sheaves? Because we want Meyer-Vietoris. This part builds in Meyer-Vietoris with respect to Nisnevich covers, so Zariski covers. So there's a nice Meyer-Vietoris property. That's preserved. When you localize, that's still preserved. So this has Meyer-Vietoris. Right? Remember what we're trying to do is construct formally universal cochain complexes. So what is a singular cochain complex? That is Meyer-Vietoris. Okay, we also have a Kunith formula that's already built in. Okay, but we want this, killing these things is giving a version of what's called the homotopy property. We want the affine line to look like the interval. So we don't want to distinguish between x and x cross an interval. So that's why we killed this. Now, why do you invert this thing? David, I'm glad you asked. The point is this. This is what allows for the Thom isomorphism. So that's an important property of singular cohomology, is the Thom isomorphism. It enables you to change relative cohomology to cohomology of the Thom space of the normal bundle. And in order to do that, this is the simplest case. This Z of 1 is more or less, tensor product with Z of 1 is more or less the Thom space over the trivial bundle. And once you've been a trivial line bundle, because what's the Thom space? It's over a trivial line, just over a point. It's the affine line modulo the affine line minus 0. But that's almost the same thing. That's by excision, that's the same as the projective line modulo the projective line minus 0. But the projective line minus 0 is the affine line, so that contracts to the point at infinity. And that's exactly what this thing is. This is instead of taking the kernel, I could have taken the co-kernel, because this has a section at infinity. It's this modulo infinity. And so this is really the Thom space of the trivial line bundle. And so to get the Thom isomorphism, I want to do that. Good. Okay, well.
So like
yeah.
Tate motives?
That is a Tate, yeah. So, but so the question is, why do you want to invert the Tate motive? I mean, so you have duality. And another way to say that you have duality in a local property rather than a global property is if it's because you want the Thom isomorphism to hold. And then you do get duality once you have that, but you need the Thom isomorphism to get that. Yeah. Right. So that's reflected in Grothendieck's construction of motives. He does a very similar type thing, and there it's in order to get duality in the theory. All right. So that's our category. All right, but we're still not quite there. We have to, yeah. So what are some properties here? Well, let me just make some remarks. So the first thing is you can replace K, the base field, with any, or let's say spec K, with any reasonable scheme, base scheme.
Well, you really didn't use your algebraic, your triangulated categories much.
Well, yeah, I'm kind of sweeping that under the rug. The interesting triangles here come by reflecting interesting properties of the theory. So I'm not going to say anything about that. All right. For our purposes, if we assume that actually, for our purposes, we're just going to look at schemes S which are smooth over some base field. So for example, if you restrict yourself to this case and you write down exactly the same definitions I did, the only thing you have to do is you have to replace product with product over S and replace variety smooth over K with variety smooth over S, and exactly the same construction works. Okay, so this gives you a functor from, say, smooth schemes over some base field to triangulated tensor categories, sending S to dm of S. Okay. All right. In addition, you have a motive functor. So if you take smooth varieties over S, you have a functor to this category, which takes some variety X over S to this, the image in this localized category of this representing PreSheaves. So maybe I'll put a little box around it to indicate it's not in the category of sheaves, it's in this, its image in this localized category. It's sort of the image of a complex supported in degree 0 in some triangulated category. So notice this is not, this is like, it says you have homology, because this is a covariant functor. Okay, so we want cohomology. Remember, our goal is to write down the universal cochain complex. So that follows from the fact that the objects dx are dualizable. Okay, so yeah, at least for S, well, just under some circumstances, but let's just say they're dualizable. So in other words, so let's say for S speculative field. So we have some cohomological functor H. From smooth varieties over S to dm of S. And this is my universal cochain complex. Okay. Now, what's missing, I don't have an abelian category, and I don't, so I can now take my formal bar complex of some variety and apply this universal cochain construction to it, and I get some object in this category, some total complex, which is like the bar complex on its singular cohomology. But I still don't have H0, which is what I'm after. I want to get a Hopf algebra, not some derived Hopf algebra. So this is where I'm stuck. And there's a conjecture that there's some underlying abelian category here, but this conjecture, just showed me a paper about this. But
Wait, who just showed you?
no, it's another story.
Okay.
Seems hard. Let's put it that way. But what we can do, there are some circumstances where a smaller category, in other words, if we look at special types of smooth varieties over special types of bases, then they're in a smaller category here, which does have some underlying abelian category in it. And this brings us to the triangulated category of mixed Tate motives. So what we can do, let me work just with Q coefficients. So I tensor everything with Q, and this, by definition, is the triangulated subcategory, full triangulated subcategory, generated by, and I'll write Q of n instead of Q of n, which is, I had this object z of 1, so I'll now call it Q of 1 because I'm working with Q coefficients, and I take its tensor, self-tensor product n times. So I take all these special objects, let's see, these are over the base, and I take all their tensor powers and their duals. So, and also, these are all dualizable, and Q of minus n equals QS of n dual. I take all these guys. So in other words, I take Q of n's for all n in the integers. And these generate some interesting category. So why are these categories interesting? For example, let me just, this category has a lot of information. So if we want to take the Homs in this category, so one object we have is just this Q of 0, this is just the representable sheaf for S, and then into Q of Q shifted by P. This, by definition, is the, well, it's sort of the motivic cohomology of S with coefficients. And this theorem tells us that this is isomorphic to the algebraic K-theory of S in degree 2Q minus P in atoms weight Q. And there's an integral version of this also. The integral motivic cohomology exists with a similar formula. But I just wanted to point out that, so this category, even though I define it in kind of an abstract way, it recovers algebraic K-theory. So it has a lot of interest in this category for that reason. All right, so let's see. Another structure that this category has is inside, I can look at the subcategory of things of weight less than n. Keep getting, yeah. S, here. This is the triangulated subcategory generated by these special objects QS of minus m, where m is less than n. So it's a smaller category. And the theorem here is you have a truncation functor. This looks just like Hodge theory, but for a very special type, just for Tate objects. So in fact, there's a truncation functor here, which I'll just call weight, the weight less than n part. For those of you who know about Hodge theory, this would be the weight less than or equal to 2n in Hodge theory. So to avoid doubling everything, I just use the n's instead of the 2n. And these things give a canonical tower if you have any object m in this category. You get a finite tower, the weight less than n0, say minus 1 of m, will be 0, and that will map to the weight less than n0 of m, maps to the weight less than, let's say, some n1 of m, which will be m. So you have a finite tower. Again, the difference between being in an abelian category and a triangulated category is you just have maps. You don't have, it's not an inclusion, they're not injections or anything like that. But what you can do, you can take the associated graded, you can take the weight less than n plus 1 of m, map it to the weight less than n of m, and then one of the axioms tells you you can always complete that to a distinguished triangle, and in fact, it's a canonical completion. There's a theorem going on here, and you get the associated graded. This, in some sense, is the quotient, or the cofiber of this map.
How do you know how big n can be?
You don't, given that m, what m is. It's hard to tell exactly what the limits on n are. You can do that for any n. Usually you get 0. For all but finitely many n, the associated graded will be 0. All right, so you have this weight structure. So, let's see. I'm slowly getting to the punchline here. Oh, I'm running out of time, of course.
You know we started at least about 5 minutes later.
Still running out of time, but okay. Either way you look at it, it's very kind. But
That's how big n can be.
Yeah, right, exactly. Okay. So, great. Now, there's an abelian category here. So that's 6. Now we need an assumption. Let's assume the so-called Bailenson-Soulé vanishing conjectures, which says that when you take the motivic cohomology at S, the rational motivic cohomology, this is 0 if Q is positive and P is less than or equal to 0. Okay, it's known. So let me just say this is hardly ever known, but it is known if S is spec F and F is a number field.
How old is this conjecture?
It's, I think, from the 80s. Okay, so we assume this. Then, so the technical term is there's a T structure on this category. But I'll just say there is a nice abelian subcategory, mixed Tate motives over S inside of this triangulated category, inheriting, so duality, tensor structure, weight filtration, and this, the remarkable thing is if you take now the associated graded, the direct sum of the associated graded over n, the functor from this guy to where? Well, here's the remarkable thing. When you take the nth graded piece, you're looking at a Tate motive of pure weight n. Turns out that category, if you look at it in here, is just Q vector spaces because there are no non-trivial maps other than identity maps between such motives. The map from Q of minus n to itself is just the identity, and there's no maps if you take a shift. So what it means is that this thing actually lands in the category isomorphic to finite dimensional Q vector spaces. And this thing is what's called, whether you just call it 2 or W star, is a fiber functor. In other words, it's an exact tensor functor which is faithful. And what that gives you, now you can get a concrete version of this. So now we get a group. So the whole theory of Tanakian categories, which I unfortunately do not have time to say much about, Tanakian duality says that there is a pro-algebraic group scheme over Q, let's call it GS, such that mixed Tate motives over S is equivalent to the category of finite dimensional representations in Q vector spaces of GS. So it's kind of concrete. Okay, so now I can make our construction. So let's look at the follow. So here, let's take an example. Let's take S to be spec of F, where F is a number field. And let's take X over K to be some smooth K variety with the property that when I take its motive, this is some object in this, let's take it with rational coefficients, this actually lands in this subcategory. It's a Tate motive. So X is a Tate motive. And let's say we have some K point X.
K equals that?
Yes. So let me call this. Thank you. Okay. Then we can do the program which I was kind of alluding to. Then we can form we can take the loop space of X on X, which is just X spec K. We have the two maps, which is just both X into X, and then you have various diagonals, etc. You have this cosimplicial gadget. You can then take its motive. The theorem is this thing is an in-top algebra in EMT. Okay. This is because Tate motives satisfy the Kunnert formula. And so what is this thing? This just looks like H of spec K. It looks just like the bar construction. H of X h of x tensor 2, etc. So it just looks like the cochain complex of the bar construction. Now, since it's in here, you can take h0 of it. So you can define sort of the motivic bar complex of h of x. You can take h0 of it. Call that chi. Right, h0, I forgot to say, that since we have a T structure, there's a cohomological functor, h0, taking the sort of zeroth cohomology in this triangulated category and giving you something in the abelian category. Sorry, I forgot to say that. So you can take this motivic h0, it lands, this will then be a Hopf algebra object in mixed Tate motives over K. And then this is how Levine and Goncharov define, so I'm almost done, what I wanted to say. So this is the definition of Levine Goncharov. The motivic of the Levine Goncharov pi 1 of x with base point x is just formally you take this Hopf algebra and you take just the affine group scheme associated to it, which is just a formal, you just work in the opposite category, it's just a formal notation. So that's the construction of Levine and Goncharov, and now our main theorem is the following. So I won't be able to tell you how the proof goes, but we recover the fundamental exact sequence. So if x itself satisfies valence and Soule vanishing, okay, then we can look at the category of Tate motives over X and the abelian category inside the triangulated category, and that's going to be given as the representations of its fundamental group, of its Tanaka group. So that gives us this group GX. And the projection to spec K, well, K also satisfies valence and Soule vanishing, so it has this group. Just remember, as the Tanaka, this is equal to the Tanaka group or Galois group of the category of mixed Tate motives over X. This is equal to, if you like, the Galois group of the category of mixed Tate motives over K. This is induced by the push forward. Then we have a map here given by the point. And the kernel of this push forward map is exactly the Levine Goncharov pi 1. So we have the fundamental sequence. So this is the group which, if you replace X with its C points, gives you something that looks like the Malchev completion of that topological space. And that sits in as the geometric part of the group whose representations gives you Tate motives over X. So you can, let me just conclude by saying it has the following interpretation. So the corollary of this is, I'll phrase it in a rather loose way, it says the category, under these assumptions, the category of Tate motives over X is equal to the category of unipotent local systems over X with fiber in mixed Tate motives over K. So a little bit of a grain of salt here, but that's the idea. Right, so in other words, what's a representation of this group? It's a representation of this group, that's just a local system on X, together with a representation of this group, that's just a mixed Tate motive, and that's giving you the fiber. And there's a certain compatibility between the local system and the representation here, which is encoded in the, so it's a unipotent local systems, sort of where the monodromy and monodromy automorphisms in this category. You can say it that way. Okay, well that's it. Thanks very much.
Thank you. Are there, I'm trying to get out of the way. Are there questions?
Couple.
Yeah.
So, could you say a little bit more about how you get Maya Viatoris and Cooney formula?
Yeah, I mean, it's pretty formal. It's kind of, it's...
No, I'm shocked.
Yeah. I mean, Meyer-Viatoris follows just because you have, you're taking the derived category of Nisnevich sheaves.
Yeah, well, that's what you said before, but could you?
Okay, so what does that mean? Let's see. Well, yeah, it's, I lied a little bit, right? You have to, I mean, there's a theorem hiding there, but it's a little, yeah, so I can't really explain without going into quite a lot of detail, but it really follows from the fact. Okay, so it's partly because you're taking Nisnevich sheaves, and partly because there's a nice property of correspondences in the, if you localize in the Nisnevich topology, it follows from Hensel's lemma that if you have a correspondence, it's just the following picture. So here you have a correspondence on X, parameterized by some W, by some Y. So here's a correspondence. Here's your W. Okay? And you write X as a union of two pieces. Okay? And so you want to say that the sheaf X kind of splits up into the sheaf for U, the sheaf for V, and with a compatibility along the intersection. So it means if I have this correspondence here, I have to be able to write it as coming from a correspondence on U and a correspondence on V. But there's a finiteness condition. This has to be finite over Y. And if I just restrict this W to U, it's no longer going to be finite over Y. So that's kind of a problem. But if I take Y to be Nisnevich local, which means it's just the spec of a Hensel ring, then, so let's take some point on Y and then take spec of the Henselization of this local ring. Well, we know from Hensel's lemma that the irreducible components of the restriction are in one-to-one correspondence with the points over Y. So each of these points either lie in U or lie in V, and then it breaks up into some pieces, so I can write it as some pieces coming from U, some pieces coming from V, and where was the ambiguity? Well, they're in the intersection. So that's essentially how you prove. I mean, it follows from that fact. Yeah.
That's good. So,
and Kunith is, you define it that way. So, right. So I didn't tell you how you define that. So what I slid under the rug is that the tensor product is not the tensor product of sheaves. Okay, so you define, you make the following definition. You define the tensor product of these representable sheaves is by definition the representable sheave of the product. So you impose Kunith formula by definition. And then it's a standard, if you have a sheaf, it has the canonical surjection from a direct sum of representable sheaves. Right? Because what's a section of a sheaf? It's a Hom of a representable sheaf to the sheaf. So each section gives you a Hom. You take all the direct sum over all x's and all sections of your sheaf F on X. That gives you a surjection from the direct sum of these guys onto F. And then you can repeat that with the kernel. So you have a canonical resolution of any sheaf by representable sheaves. So you take two sheaves, you take their canonical resolution, that looks like a flat resolution for this tensor product. You take the tensor product, you take the H0, that's the tensor product of those two sheaves. And so you've extended the Kunith formula to work on arbitrary sheaves. So it's kind of a cheat, but you force it. Yeah.
The other question concerned your choice of base. You worked over a field. Surely reduction mod P is of some interest.
Yeah, certainly it is. Certainly it is. So the story is that the general theory was kind of as I outlined. There is, in fact, a functor from any category of reasonable schemes. Whatever, separated or something. I mean, you don't need them to be over a field. You don't need them to be smooth or regular or anything. There's some reasonable category of schemes which is quite large, a contravariant functor of two triangulated categories. So that the problem is you want that to look like the functor which takes a space to its derived category of sheaves, a topological space. So you want it, in other words, to have this formalism of f upper star, f lower star, f upper shriek, and f lower shriek. These Grothendieck 4 functions. Yeah, and then Hom and tensor product, the 6 operations. So, in fact, this, as far as it's known if you restrict your schemes over a field, which for your purposes is not good enough. And there's a beautiful paper or asterisk volume by Joseph Ayub where he does essentially all of SGA4 in a formal setting. And he gets some certain axioms for if you have a functor from a category of schemes to triangulated categories satisfying certain axioms, then out of the f upper star and f lower star and some adjoint properties of those and a few other types of things, then you get the whole, you get at least these 4 operations. The monoidal structure, Hom and tensor product is some additional stuff. He also talks about that. Okay, but there's a certain locality property that's needed with, if you have a closed immersion, you want the sheaves on X to look like sheaves on the complement and sheaves on the closed subset. And I think that the state of the art is that if you're really working with integer coefficients, this part is known if you're talking about, say, smooth schemes over base schemes over, or maybe even schemes over a field. In mixed characteristic, there seems to be some, it's an open question, I believe. However, with rational coefficients, it seems to be okay. There's another category you can look at, this stable homotopy category, which does have all the properties you want. And then the category of motives with rational coefficients sits inside as a summand. So I'm not absolutely sure, but I believe if you allow yourself rational coefficients with some technical difficulties, that story is okay. With integral coefficients, I think it's still an open question for motives.
Good. Thank you.
You're welcome.
They're not expecting us across the street for dinner for another 15 minutes. So are there other questions? Or?
But
yeah.
I'm not sure if it makes sense, but this Motivic I want, right? Can you pursue the analogy with the topological pattern? For example,
Yeah, let me give you an example. Maybe if I show you an example.
Okay, then I have the questions.
Oh, okay. So let's do
maybe the example will answer them.
Yeah, let's do the example. So let's take K to be Q, so we have some arithmetic interest, and we'll take X to be P1 minus some finite set S, so S inside of a set of rational points. So then, this pi1 dg of X, if you view it just as a group scheme over Q, so let's say if you apply this functor to it, so this is really as a group scheme over Q. This is, it's a unipotent group, so it comes from a Lie algebra. So when we take the Lie algebra of this is just equal to, it's the free Lie algebra on generators S modulo the relation that the sum is 0.
Okay.
It's the same as it's the nilpotent completion. usual bit of the Freely algebra on S modulo the sum S. Right. So it's the usual, it's the real topological thing.
Okay.
Okay. Now that's this part here. But the interesting thing is that you get a this thing is non-trivial. It's highly non-trivial. So what's this? Is GK. Well, this comes from Tate motives, and Tate motives have extensions, and then they have the Tate twist. So the Tate twist gives you an integral grading on things, and that introduces a GM quotient. That's kind of uninteresting. So there's a GM quotient of this multiplicative group quotient, and then you have this kernel, which is the interesting part. This is again a unipotent group. So it's determined by its Lie algebra, and this again is a free Lie algebra, free nilpotent. It's the nilpotent completion of a free Lie algebra on over Q on generators. Well, we have one generator for each prime, and it's graded. That's the GM gives you a grading on this. So this is in weight -1. And then you have one generator in each odd weight, where this is in weight -3, -5, -7. So so let's look at this sort of the simplest case, where you take x to be p1 minus 0, 1, and infinity. And then you take this x to get the action, you take this x, and you can actually take this to be the so-called tangential base point. So the direction at 1, say. So x to be this partial with respect to t at 1. And then everything is defined over the integers, and what that means is that these act trivially. So these, the primes, that tells you how things ramify. It's when it would be, in general, when this rational point kind of goes through 0, 1, or infinity, those are the primes that will occur in here. So then the p's don't act, p's act trivially. And no one knows how the rest of it acts. Well, okay. People have partial information, but how, the full story of how the rest of it acts is unknown. So this is related to a conjecture of Levine and Ihara. Their conjecture is when you look at the action of this free gadget as outer automorphisms of this free nilpotent group, then it's injected. It injects into the outer automorphism group. That's not. So what was your question?
Two questions.
Two questions.
Maybe I'll wait, but first off, is there something like a Hurevich map from this pi1 to some kind of h1?
Ah. Let's see.
Like the universal development algebra of the abelian, free abelian Lie algebra in this case.
Right. Yeah, I think there's a map from the dual to the h upper one with z1 coefficients. So that's something I'm trying to understand. I don't quite understand it, because there's a twist that comes in. So the abelianization, like in this case, the abelianization are just the units, modulo scalars, right? And the units are something in h upper 1. So, how do you get something in, the dual of the abelianization. So every unit you can view as a map to GM, which is a map to the circle, and that gives you a Z tower, right? So that'll give you a character, but then in topology, that gives you a character of the fundamental group.
Okay.
So the H upper 1 gives you characters, but it's H upper 1 with Z of 1 coefficients. Gives you character, right? So there's a twist, which probably what I'm saying isn't quite right, but there's the fact that the natural things which occur in topology are twisted homomorphisms, not characters, makes life interesting. And I don't quite understand how that works.
Okay, and then briefly the second question, is there an analog of formality here? Like, do you know when this Maltsev the algebra, or the analog of this Marx algebra is quadratic?
Well, there's a conjecture, again. The conjecture is that these Lie algebras, when you take the Tanaka groups for mixed Tate motives over a field, they should be, they should be formed. They should be actually k-pi 1s. So they should be 1 minimal. That's the
Always?
case. Yeah. And unfortunately, I mean, so in the case where they're known to exist, right, you have this condition for them to exist, which is this vanishing conjecture for the field. That the Motivic cohomology of the field in negative degrees and positive weights should vanish. And this is known for number fields and, you know, like something like Q bar join one variable. That's about all it's known for. So under those cases, you can ask the question for those, because you don't even have the groups outside of that case. For the number field, it's almost trivial because it's a free group. So it follows from the vanishing of the H2 vanishes. So it's just like in topology. And I think there's a similar story, although I'm not sure. I don't even know if the case of Q bar adjoint a variable is known. So I shouldn't say. I think there's, seems to be open. This one minimality conjecture seems to be open even in that case.
So there is room for thought here?
Oh yeah.
Not just room for more conjectures. All right, well maybe we should thank Marc again, and if there are more questions, you can take a pad of paper and begin it.